Our last speaker today is Lavanya from IIT in Madras, where she is a project officer on a process of verification in Python. With a background in MS at IIT Madras in Chennai, Lavanya has predominantly worked in various process of verification teams with IBM, ARM, and Rambus for around 7 years. For the past 3 years, she has been leading verification efforts at IIT Madras with a Shakti team working on research and development efforts on RISC-V based processor systems. So over to you. Lavanya is based in Chennai. So over to you, Lavanya. Thank you.
Thanks, Mike. Sarah, can you just check if the presentation is...
Yeah, we can see the agenda. So
okay.
Yeah, go ahead.
I have lost... Yeah. So, hi, everyone. I'm Lavanya. I'm not having control over the presentation, that's why.
Yeah, go ahead, Lavanya.
Yeah. So, hi, everyone. I'm Lavanya from Shakti IIT Madras. It's a research group working on processor development and its ecosystem. And at this DV talk, I'll be presenting how we use Python for processor verification. The agenda of today's talk is providing you a trend on processor adoption and its verification. Along with that, I'll be giving a brief introduction of our Shakti efforts and the processor verification components that we use for those processor development, and where the Python packages for verification comes in, and finally ending up with why we decided to go with Python over the traditional verification methodologies. Okay, so when we see the trend, we see that as per the Wilson Research Group survey presented in the RISC-V Summit in 2020, we see that an increasing number of processors are adopting the RISC-V ISA, and nearly a quarter of the designs have RISC-V in it, both FPGA and ASIC combined. RISC-V consortium itself has 1,000 plus members, and it has made available around 124 RISC-V cores and SoCs open source for adoption in the market. This is an increasing trend, and this is supposed to grow, is the prediction. And similarly, when seen in the Python side, verification methodology side, we see that Python has been included as part of the tracking in the verification methodology. There has been already existing UVM environment with the system Verilog UVM environment. Along with that, this time CocoaDB has been introduced for tracking purposes in this survey. So when we see that these two trends take us to the Shakti-based processors, where we have Shakti E-class, C-class, and I-class processors. And this is where we want to build the state-of-the-art processor along with the state-of-the-art verification methodology. We have had different class processors targeting application domains from IoT, compute applications, and performance-oriented applications. And for that, we have also taped out test chips in E-class and C-class. Our out-of-order processor will be for consumption soon when we release it in open source. In all these processors, what we have is a common verification framework. And we also strongly believe in having an open source tool flow to have that verification in place. Our design is a BlueSpec system Verilog developed design, and the generated Verilog is simulated in the Verilator. And this verification environment around this setup is commonly used across the various class of processors, namely the E, C, and I class cores, maximizing the reuse. What are the various different components? I'll be getting into in the coming slides. As part of this verification, we have a comprehensive suite of directed as well as random tests. What kind of tests we use, and the generator that we developed and in-house for aiding this processor verification. I will also touch upon that. So in order to just introduce the concept of process verification, we see that it happens at the ISA level, the instruction set architecture level, as defined by the RISC-V International Consortium. And once the design is implemented, we develop the test suite, which is in RISC-V assembly programs. Along with that, we have a lot of generators generating the RISC-V assembly, trying out different random scenarios to stress test the processor. This test suite gets compiled with the tool chain, and then it's fed into the design as well as the reference model. The process state comparison between the design and the reference model brings out the checking that happens at every instruction execution. There is also an end of the test memory check that determines whether the test has passed or failed. This is the overall abstract level setup of Shakti processor verification. And we will go into details of all these components one by one and how we use Python in that. So to start with, we have assembly programs, but along with that, we have the program generators. We have an inbuilt automatic assembly program generator, which is developed in Python. That gives us a strong way to automate a lot of configurations that are supported in the RISC-V architecture itself. We have a configuration YAML file that is provided as an input to the generator that generates based on that configuration targeting a particular implementation of the RISC-V ISA. The automation and the configuration we are able to do very easily with the Python. And although this tool chain is built in C, C++, the whole framework of generating the tests and then compiling them in a parallel fashion, we use Python framework for deploying that. So that's why it's mentioned here. The scripting framework around the verification is also can be built in Python, which gives us massive ease of adoption. The most important part of this verification component is the test bench, where we instantiate the design and also the reference model and make them compare the process states. In that, we use an open source Python package named CocoaDB. It is coroutine-based co-simulation test bench that aids us in hooking into the RTL simulator to explore all the design hierarchies to set or monitor those values. And hence, this gives the control over the DUT. Along with that, we also have the reference model where we have the instruction set simulator known as Spike, which is again openly available, the C++ model. When we run it along with the reference model, this can be easily integrated with our Python test bench, and the state level comparison happens at every instruction execution. Moving on, once this whole test bench setup is done, we deploy a huge regression flow, which is highly automated using continuous integration in our repositories. In this also can plays a major role by helping us automate a lot of things that we do. This brings in massive parallelism because we have used all the open source flow till now, and we are only restricted by the compute resource of the where the framework is run. So verification is never complete without the coverage collection. So for coverage, we use Verilator-based code coverage collection, where we see how good our tests are running. Along with that, we have another Python package which we use. It's again open source package, CocoaDB coverage, that helps us define the functional coverage definitions. Along with that, the CocoaDB coverage also provides some methods for defining the constraint random generation. So in short, everything that happens within our process verification is one way or the other is aided by the Python language. And we have found it helps us in quick bring up of a process verification and also massive reuse across different class of processors. So going back to answering the question of why having this COCO-TB validator setup over traditional methodology that is so prevalent in the industry. It feels so. From our experience, we have seen that this framework can be quickly ramped up with the students who stay with us for a short time, contributing to our verification, and also with open source contributors who with whom we interact on a regular basis. This also helps us in having a flexibility in setting up the framework in remote workstation. So the contributors can themselves have the setup done within half a day or so. And the ease of integration that helped us with integrating with any external reference model for verification, be it MATLAB, be it C++, the huge Python ecosystem that helps us integrate all these reference models and also reuse whatever that is developed within Python has been a big plus. Like, for example, in our crypto verification, we have used existing Python libraries for functional verification. That said, whatever we have done with Python, we have made sure that it does not compromise on the verification quality that we want to get it for a design win. And as I mentioned before, the Python also helps in massive simulation parallelization. Like, for example, if I want to simulate a test in, let's say, a many core machine, I'm only restricted by the compute capability and not with any of the verification tool chain availability. So these are the reasons which has majorly helped us in adopting, along with, of course, the most important part, the validator simulation. The COCO-TB validator setup has helped us in adopting an open verification flow for processor verification. As I said, again, diving back into the COCO-TB environment, what COCO-TB stands for is it gives us a standardized interfaces like VPI, VHPI that provides hooks to the Oracle simulator. And along with that, the library also provides some test bench components like drivers, monitors, and scoreboards, which helps us quickly bring up our UVM-based verification environment. This has helped us in a quick bring up in, let's say, a small block level verification where we wanted to target. We quickly brought up the test bench environment in a day, and our efforts were concentrated on bringing up test writing according to the test plan that we had decided, and also defining the functional coverage definitions for which we will be confident that that block has been verified. So when we look at the flow for the processor verification, the Python has permeated into all different stages of our flow, and hence we can readily say that we have adopted verification Python in our as a major component in our verification. To conclude, this is a code block just to give an illustration of how we use it. All these are open sourced and it's available in our project repositories. So this is just an example of how we use COCO-TB coverage to generate our functional coverage metrics. And this also provides, this helps us define the cover points and also the cross covers of the features that we want verified. This is an example of targeting only a part of an instruction set. Like, let's say, for example, regarding the bit manipulation instructions. It's a 32-bit instruction that has to have been covered, but the valid paths are a very small subset of the whole 2 power 32 combinations. So we provide the functional coverage definition for the valid cases using the COCO-TB coverage. And once the simulation is running, we collect individual coverages and merge it. We believe in massive reuse. It's not just about the codes that we develop, we reuse it. Since it's Python, we massively reuse already existing Python ecosystem packages for our verification efforts. So our code maintenance massively reduces to what, how much we reuse, and then we maintain it for our own customized verification environment. Third, sorry. Thus, in conclusion, what we would like to, as a Shakti team for the verification, process verification efforts, what we would like to claim is that risk-free process verification, when it leverages the CocoaTV Verilator setup, it brings in very competitive industry standard open source methodology without compromising on any verification quality. This sets up our Python-based environment for rapid and cost-effective design wins. Future work which we would like to explore. Currently, our CocoaTV Verilator setup supports block level verification and also core level verification. We would like to also explore the use of Python at all other abstractions levels, like say at the system level, and then bring it in our use. In that regard, we also are collaborating with Inco Semiconductors and TESOL for Shakti C-class SoC development work, and we hope to support this setup, the open source verification flow, which aids our new reality, which brings in the new reality in verification environment. That's all from my side. Any questions?
Thank you very much.
Thank you, Mike.
Yeah, no, thank you very much. And as you mentioned there, we are collaborating with Lavanya and Incor. We're doing the CPU verification based on Python at TESOL in our offices in India. Close collaboration with Incor and Lavanya. So, and using all these Python tools which Lavanya mentioned in her presentation. We do have time for one question, Lavanya, so I'll just read out one of those. This is a question regarding MATLAB. Have you tried integrating MATLAB with Python directly?
No, I have seen examples of it. We haven't found a use case with MATLAB in our work yet.
Okay. Okay. So thank you very much for your talk. And we'll now move to wrapping up. Thank you very much, Lavanya.
Thank you.